Well, we come now to the study of gravity as formulated by Newton. So we have a picture here of a modern apple tree, and perhaps descended from Newton's apple orchard. Newton did grow up at a location that had an apple orchard, probably was not laying up under the tree and being hit on the head by an apple, but certainly would have seen apples fall from the trees and applied some physics reasoning to this process. Gravity, this attraction from the earth on the apple, caused the apple to fall down. Newton extended this out to the moon, and that became important in confirming Newton's law of gravity. So, what is that law? Well, the force of gravity, as described by Newton, is a constant, capital G, the universal constant of gravitation, times mass 1 times mass 2. These two masses are attracting each other. Mass 1 applies a gravitational force on mass 2. Mass 2 applies a gravitational force on mass 1. Consider those Newton's third law paired forces. They are the same size and opposite in direction, and they act on different objects. We must then divide by the distance between the centers of the objects, and we're just going to assume we have circular or spherical objects. So Gmm over r squared, Newton's universal law of gravitation. The capital G is a constant, 6.67 times 10 to the minus 11 in the metric units. Newton did not know the value of capital G. It was over 100 years after this law was described that a measurement was made of capital G in a laboratory. The G is a constant, multiplied by the two masses, each in kilograms, divide by the square of the distance between the center in meters. R is in meters, the M's are in kilograms, and we can get newtons then of force. So here's a drawing of this process with the two masses. They have lowercase m, capital M here, instead of M1, M2. But we see that the force is attractive. It acts in a radial direction directly between the centers of the two objects. So that's our situation for the force direction. Of course, force is a vector and has a direction. So one thing that we can consider would be kind of proportion problems. If we would double the mass, what would happen to the force? If M1 doubles, what would happen to the force? We'd have an extra factor of 2 in the multiplication, the force would double. What if we would double the distance between the two objects? If we leave the masses the same, but double the distance between the two objects, well, we'd have to substitute in place of r here, we'd have to put in 2r and square that quantity. That would end up being a factor of 4r squared in the denominator. Our force goes down by a factor of 4 if we double the distance between the centers. If we would triple the distance between the centers, that would be 3r quantity squared. That'd be a factor of 9 after we squared the 3. The force goes down by a factor of 9. If we have 4r between the centers of the two objects and the mass is the same, that'd be 4 squared, r squared, 16. As a new factor in the denominator, our force would be 16 times weaker. So the force gets weaker faster than you might expect. If the radius increases by 5, the force decreases by a factor of 25. If the radius increases by a factor of 10, and maybe I shouldn't say radius, but the radial distance, the distance between the centers increases by a factor of 10, the force goes down by a factor of 100. So just keep that in mind. So we have all around the world things that are dropping towards the ground, and they drop towards the center of the Earth. And all around the Earth, there's very little change in the distance to the center. On mountaintop, you're a little bit further away, so the force of gravity is a little bit weaker. In a deep valley, Death Valley in California, below sea level, then you're a little stronger gravity, but it's not a big effect, a very minor effect. And we have a situation coming up here where we can use this information on gravity to get some clue about orbits that take place. Now, before I do that, let's talk about this a little bit more. Suppose you measure the force on a tennis ball. Well, let's say an apple. Let's say you measure the force on an apple at the surface of the Earth, and you know the mass of the apple in kilograms, and you know capital G, and you know the size of the Earth, the radius of the Earth, m2 being the mass of the Earth. Is it possible to calculate the mass of the Earth? And the answer is yes. So this is the way that we know the mass of the Earth. By measuring these other quantities, we can come up with the mass of the Earth. And again, this r squared factor here, as Newton worked with just proportions, he did not know capital G, so he did not have an equation. He had a proportion. Force is proportional to m1 times m2 over r squared. With calculus, it can be shown that this 1 over r squared dependence creates an elliptical orbit. Now, this work is being done around 1670, 1665. Newton had available the results of Kepler, and his orbits of the planets were elliptical orbits. This law of gravity generates elliptical orbits. The way this force behaves with gravity from the sun on a planet causes elliptical orbits to take place. The r squared here, Newton, from the orbit of the moon, could calculate the acceleration of the moon. Of course, force is proportional to acceleration, but the centripetal acceleration of the moon, v squared over r, that acceleration turns out to be 1 divided by 3,600 of 9.8 meters per second squared. So a factor of 3,600. From astronomy observations, Newton knew that the distance from the center of the Earth to the center of the moon was roughly 60 times the radius of the Earth. So the acceleration in its orbit for the moon is a factor of 3,600 smaller than the acceleration at the surface of the Earth, smaller than that 9.8. And Newton could work out that this r squared was a reasonable factor, with r being a factor of 60 to the moon, bigger than the r at the surface of the Earth, and the acceleration at the moon being a factor of 60 squared, 3,600, smaller. That confirmed to Newton that r squared was correct. So back to orbits. For objects orbiting the Earth or objects orbiting the Sun, for our purposes in this course, we're going to take them to be circular orbits. So we will use the results of uniform circular motion, and this force towards the center caused by gravity of the Earth on a satellite around the Earth, or gravity of the Sun on some object moving in a circular orbit around the Sun. Of course, that centripetal force is the mass of the object that's moving times its centripetal acceleration, v squared over r. And we have the force now in this chapter being supplied by gravity. So gravitational force creates the centripetal force, and you can do a substitution here. You can do a substitution, replace this F sub c with the force law of gravity, and do a little bit of algebra, solve for the velocity. The masses will cancel. The mass 1 here would be a satellite, mass here would be a satellite going around the Earth. The masses will cancel, and the velocity for this circular orbit is the square root of this gravitational constant, the mass of the body that has something going around it. So for an Earth satellite, the mass of the Earth. For something going around the Sun, this is mass of the Sun. And then divide by the size of the circle. Take a square root of that information. This gives you the speed of something in a circular orbit. And you should do the algebra here, kind of confirm that you do produce this. And hopefully ask someone a question if that does not work out. So this has become very useful in astronomy, as astronomers find something that's orbiting something else. They can calculate the mass. So around 1980, a moon of Pluto was discovered, and actually 1978, the information on the orbit of that moon allowed astronomers to calculate the mass of Pluto and discover that Pluto has less mass than our moon. And a sequence of things that got Pluto got demoted then into dwarf planet status. If we want to know the period for the orbit, so capital T here would be the period for the orbit, we can replace the velocity with the distance traveled divided by time. Circular orbit, 2 pi r is the circumference, divide by the period, and we find that the period squared is equal to 4 pi squared r cubed over capital G and the mass of the object. Very useful again in astronomy. We talk about the period squared equal to the size of the orbit cubed in astronomy. This is a little bit more exact. It gives a little bit more information because now we can change this to if it's something going around the Earth or something going around Pluto or what have you. This can be used to solve for various unknowns. But there is a relationship that you should be aware of. In a circular orbit, the velocity is the circumference of the orbit, 2 pi r, and then we divide by the time for one orbit, divide by the period. This plays a role in communications for the Earth, the geosynchronous satellites. So many homes have a satellite dish installed on the roof or on a post out in the yard, and that satellite dish points towards the satellite going around the Earth. I think the distance is around 22,000 miles. In my class, we'll probably work that out. But if you take the period of the orbit to be 24 hours, then the Earth turns once in 24 hours. The satellite moves around the Earth once in 24 hours. And the satellite dish does not have to track from horizon to horizon the satellite. The satellite dish can point just to one spot on the sky. And the communication satellite is always correctly aligned with the receiving antenna, the dish antenna on the roof. So geosynchronous satellites, this is above the Earth's equator, and there are many, many satellites in orbit around the Earth at this position. Many countries take advantage of this for putting up communication satellites. So geosynchronous orbit, there's one orbital period of 24 hours. The satellite stays in place for a long time. You don't have to readjust your antenna. There are other satellites closer to the Earth, the GPS satellites, and they do track across the sky. They're closer to the Earth. We get a little higher power from the satellites into a cell phone or something that needs GPS information. So you can look up some information that in Wikipedia. Then go a little further here. This is a graphic that shows the center of mass of the Earth and the Moon going around the Sun. The Earth goes back and forth around the center of mass orbit. So why would that happen? Now, because the Moon is over on the other side. It's kind of a seesaw playground type phenomenon. The center of mass of the Earth-Moon system is here. The Earth goes from one side to the other of that center of mass system as the Moon goes from one side to the other. This is not to scale. This wiggle is a lot bigger than actually takes place. The Moon, however, does significantly go back and forth across this center of mass path. Of course, that happens because the Moon has less mass than the Earth, so it gets accelerated more than the Earth. Maybe going back just a little bit here too, this circular velocity. What if we wanted something to escape from the Earth or escape from the Sun? Now, it turns out that if we up the velocity to a number called the escape velocity, then we'll have an object that leaves the Earth or leaves the Sun And it turns out that you just multiply this circular velocity by square root of 2, and you achieve escape velocity. So multiply the circular velocity by square root of 2, and you get escape velocity. This has been done, of course, many times for satellites leaving the Earth, spacecraft leaving the Earth and going to other planets. It turns out it's been done 4 times for spacecraft that are leaving our solar system. So the 2 Pioneer spacecraft and the 2 Voyager spacecraft have enough velocity, were given enough velocity to escape from the Sun. And the Voyager 1 spacecraft has actually reached a location where the Sun's magnetic field is no longer dominant, but instead the galactic magnetic field is dominant. So some people say that this satellite has left our solar system. It's way beyond Pluto, but it has given us information that there's this boundary of magnetic fields. We'll talk more about magnetic fields in the second semester. So let's go a little bit further here. How do we achieve an orbit? Well, we might fire a cannon with just a little bit of gunpowder. It'll go out but land at A. We're on some tall mountain here. We fire with more gunpowder, we go to B. We fire with more gunpowder and we achieve this circular velocity, and we have an orbit. Or D, we fire a little bit more gunpowder, we get elliptical orbit. And E, we achieve escape velocity and never come back to the Earth. So we have various orbits depending on the speed. For the circular orbit C, is there any centripetal force on a spacecraft in a circular orbit? Is there any centripetal force on a spacecraft in a circular orbit? The answer must be yes. The velocity is changing direction, there is acceleration, and there is a force towards the center of the Earth. So in a sense, the satellites are always falling towards the Earth. They're being pulled towards the Earth. There is no counterbalancing force. The net force is towards the center of the Earth, the centripetal force. But as they're pulled towards the center of the Earth, they're moving forward at roughly 17,500 miles an hour. And as they move forward, the Earth curves away, and they never hit the Earth. So they're always falling towards the Earth. You can see we've fallen to the other side when we get back to the mountaintop. But the forward motion maintains an orbit, and we never hit the Earth. So this has been taken advantage of it. Rocket scientists have been working a long time on how to achieve orbit. This is from the mid-1950s, I would suppose, and thinking about getting satellites into orbit around the Earth, first for political reasons and then for scientific reasons. But the Soviet Union put Sputnik into orbit in 1957, caused a little bit of a panic that they could put material into orbit, and this is Cold War era. The thinking is they could put a bomb into orbit and drop it back to the Earth where they wanted. So the United States also had a space program in January 1958, successfully put a satellite into orbit, and it did have some scientific purpose to it, to measure the amount of charged particles with a Geiger counter. So on the right here is Werner von Braun, lead rocket scientist who was a key scientist in the German rocket program in World War II. In the middle, Dr. James Van Allen from the University of Iowa. I taught for him as a teaching assistant, taught labs for the astronomy course that he taught. It was very successful and led to the discovery of Van Allen radiation belts. Again, we'll talk about in the future when we talk about magnetic fields. More recently, we've had high technology in launches, the space shuttle that's no longer a current program, the space station that is in orbit around the Earth, and again, moving roughly at 17,500 miles an hour and about 250 miles above the surface of the Earth. And here we see the space shuttle docked to the International Space Station. In space, astronauts are not weightless. Weight equals m times g. Gravity goes out beyond the Earth's atmosphere. There is a weight, but the situation is that the spacecraft is always falling towards the Earth. This astronaut is falling towards the Earth. This astronaut is falling towards the Earth. So there's no contact force required. Everything's in free fall. So things are apparently weightless in space. And these are not superheroes. They're well trained, but astronauts look like they're floating here, but everything's in free fall, so we don't need contact with the cabin, so apparently weightless. Clay Anderson from Ashland, Nebraska, astronaut who's no longer flies into space but did good work in the astronaut program. Now, getting to this measurement of capital G in the laboratory, again, F equals G m1 m2 over r squared. So in the late 1700s, two masses were set side by side, a very fine fiber here that would twist as gravity would pull this m towards here and this m over here. Put a light source that hits this mirror, and the indicator will shift positions as these masses attract. That's the basic measurement for capital G. So that's where we're going to end for this particular video. Gravity, as formulated by Newton, F equals G m1 m2 over r squared. We can combine that with a centripetal force m times v squared over r and get some useful relationships that apply to orbits around the Earth or orbits around the Sun. So keep reading and asking questions.